My edge experience started here, almost like a decade and a half back, right? Can you imagine what we were doing at that time? We were putting SSDs back on a fast-moving vehicle in a Nevada desert, and then we put these SSDs on a bowling alley, tied to a bowling pin, right? And basically slammed a ball at it. We took it to a softball, game, and you try to pitch with a solid state drive. And why we did that? We took it to the edge because it was fun at that time. It was a marketing campaign. It was adventure with Intel SSDs, and every time we tried to boot those SSDs after that beating, right, it will actually boot up. Because anybody knows what was the reason? Because it had no moving part, right? First generation SSDs, no moving part. It was rugged. It was meant for edge. Right at the beginning, we knew that these SSDs were meant for edge. There was a marketing campaign. And now, standing 1.5 decade later, right, it is a reality. It is no longer a marketing campaign. Because not only those, the ruggedized nature of the SSD, the higher, shock spec that we had at that time, 1000 G per zero point 0.5 milliseconds. That was the SSD spec on the shock side. An HDD compared to that was around what, 250, right, G. And what type of shock will you create if you kick a football or a soccer ball? It's around like 250 G, right? So you can imagine the ruggedness of the SSDs and why it is actually from the very beginning meant for the edge. Not only the ruggedness, but also the capacity growth that both of my colleagues have talked about, the performance that it packs, right, for the right level of read intensive workload that we are talking about, and also write intensive. We're talking about QLC a lot today. Power efficiency, space and weight efficiency. Roger talked about the locality challenges, right? And we're gonna show you 3 examples where we think that conceptually these SSDs can take us, right? Talk about the form factors, E3.S. Unfortunately, I don't have the slim E1.S. You can just imagine that it is half of it, right? And it almost like a gum stick form factor, which is going to replace the M.2s and whatnot. And last but not least, what about the endurance and reliability, right? We have come a long way on the endurance, be it a TLC drive or a QLC drive. And we'll show you some of those examples today as I go over some of the detail. So here in this room, we are creating a lot of data, as you know, right? Some of the industry analysts are saying that every minute we're creating an enormous amount of pictures in Instagram, 66,000 a minute. We are creating like transactions on AWS, or we're creating transactions on Venmo or Zelle, about like $500,000 per minute. We're creating Google searches, right? Where are these going? Can they all go to the core? Probably not. I mean, going back to Roger's comment, right? Pushing the data from the edge to the core is expensive. And not only that, the other point is pushing the data from the core, from the edge to the core is not only expensive, it is also not practical because there is SLA, right? Service level agreement, latency requirement. So basically, what we are looking at is more and more these use cases. The data needs to reside at the edge, analyzed at the edge, and consumed at the edge, and that will create a tremendous need for storage on a lot of use cases. There are also definitely like low storage use cases, but we're talking about use cases where density rules, right? And there are some of the examples that my colleagues have talked about, the ADAS and the autonomous driving vehicles that run around the cities and collect data, right? There's an example of a company called Inonet. They've been in the industry for almost like 20, 25 years, right? So what they are telling us is it is not possible to keep up with the data growth, right? The data logging that they do in order to feed this information back to the manufacturer, right? And give them very rich environmental data. It is not possible to keep it up if you do not adopt a modern SSD technology like a QLC, a high density technology like our P5316 and P5336 level of drive. And these guys actually have replaced the TLC SSDs. By the way, TLC stands for triple level per cell, and the QLC is the quad level per cell. So it's more dense, right? As it is more dense, in some cases, we have some trade-offs in endurance and performance. I'm going to talk about it. Does it really matter? The other thing is they're looking for really high sequential bandwidth, right? Which the QLC drives can deliver. The other very important point here is the endurance requirement for these systems, right? So what we have seen in some of the industry study is these vehicles can actually generate up to 19 to 20 terabyte an hour worth of data, right? So what does it mean? So if you translate it with some duty cycle, you're not doing 24/7 data collection, right? Maybe like 17,600 minutes per year of duty cycle. You're looking at 5 petabyte per year of data requirement for this type of an application. Why is it important? It is important because a lot of times we hear things like, hey, is QLC SSD or even TLC SSD, is it good enough for the endurance that I need, right? So if you translate the 5 petabyte per year endurance requirement for an ADAS or AD system, you're looking at 25 petabytes per 5 years lifetime of the drive, right? Where is our drive standing? Our QLC drives, higher density drives, can actually deliver up to 200 petabytes of write during the full 5 years of lifetime, if it's sequential. If it's random, it's probably 65 petabytes. Still, we are meeting that requirement, right? So it doesn't matter what the workload is, you can generate tremendous amount of value by going to a QLC drives, which is cheaper, right? And which gives you the density, which also gives you the bandwidth. In this case, Innonet was using 28 gigabyte per second of bandwidth for their deployment. John Deere was mentioned in the Rogers example, and this is also very near and dear to my heart. There's a lot of smart ag applications where there's satellite image analysis going on, robotic systems and drones are involved. You're doing see and spray type of applications where you're collecting data, right, real time that needs to be analyzed, and it cannot go to the core, it can't go to the cloud because you're making real time decisions, right, at that time. Thinking about like 5 to 10 milliseconds of delay versus going over the network and 100 millisecond delay, right? So it is not possible. So the data needs to reside where it is being generated, analyzed, and the decision making needs to take place there. So again, from those use cases, we see, yeah, go ahead, please. Question.
Okay, I have a kind of bizarre question, but if I own one of these cars or one of these tractors, should I be preparing? What should I do? I need to do about protecting that data? Do I have to care about if it resides there?
I'm going to talk about the data protection
Okay,
and
cool.
security.
The other question is, if it's only going to last 5 years, the durability, should I be preparing and putting some money in my bank account to replace those parts in 5 years?
5 years is the standard storage, life cycle. But I mean, it's basically these are for data collection, which gets dumped into in the core at some point and then get analyzed, right? And they will replace it, right? But for your own use case, embedded use case, you're probably looking at much more than 5 years, right? So those requirements are a little bit much more stringent and more reliable. Yep.
Because if you have a satellite, for instance,
Yep.
we're not going to call back that satellite after 5 years to replace.
Absolutely. So yeah, there's use cases which will take 7 years or even 10 years, right?
And so you need to do or monitoring so that you can control the health of that.
Absolutely, you're right on track. So I'm going to talk about the health and monitoring and also the security part later on. Yep.
Set that up for you. You're welcome.
Yep. So the other use case that I'm going to talk about here is the object scale, right? So this is where it's a little bit on the core, but it can also be an edge infrastructure. Think about you're increasing your footprint from a couple of petabytes to 5 petabytes. So where do you go, right? So you need storage there. And in this case, Dell is an excellent example. F600 and F900 series of their product, they can go up to almost like a petabyte range of unstructured data, right? And they have used our QLC devices. And not only that, while deploying these QLC devices, they have looked into, from their field application traces, that what is the expected lifetime, and going back to your point, right, that how long these drives can last. They have found out that some of these QLC drives can last up to 14 years, right? We spec it at 5 years, but the real use case can actually take it to 14 years. So, which is again a testament to where the industry is heading. The QLC SSDs, the high dense SSDs, are ready for these workloads, and these workloads can really take advantage of it. And here's a example of a TCO, a total cost of ownership improvement, by deploying 100 petabyte of this class of applications. If you move from a TLC to a QLC SSD, you're looking at around 17% of TCO reduction, which is huge from a sustainability point of view, from a power saving point of view, because some of this TCO is not only dollar saving, but it is coming from greenhouse gas emission control, because you're having less rack space usage. So there's rack space consolidation, there is power efficiency and whatnot.
Back onto the, I guess, the end of the 5-year life cycle, traditional IT life cycle, where we get to the end of period and it's cheaper to buy new stuff rather than kind of either get extended support, or most companies obviously don't want to sweat it. Do you think we'll see a move in the industry now that we can accurately monitor these devices, which I'm thinking is where you're going to go with these kind of next few slides, is being able to extend the warranty based on the workload that's been running on that server, based on the telemetry that you're getting from those devices? Do you think that's going to be plausible?
Absolutely. I think reuse and repurpose is one of the key tenets of sustainability. And I think that's where the industry is heading, right? So if you can reuse for, extended usage, go for it, because you have, basically warranty is a business term, right? But you can monitor how you're using the devices more in a more, real-time way, right? And that'll give you some understanding, like how you want to reposition it or redeploy it or repurpose it.
But do you think we'll see the vendors back that up?
Yeah.
So in terms of like the vendors will actually genuinely support it?
In some cases it will back them up, but there's also, as you say, right, from going from one generation to another, there's also that need to go to the faster interface or higher density, and those things will probably take more priority. But definitely that is front and center of what we are thinking for the future. Yeah.
So one quick follow-up on that, specifically with object storage, because I know that's a sensitive place as to, where do I write if it's a distributed object storage? Where do I write within there? Can be a challenge. I'm curious if, and you don't have to go in depth in this, but is there work being done towards being more in communication with the application? So being able to take, I've got this big Ceph cluster, and I've got 10 different hosts with 20 drives each. Where should I put this block of data that can best extend the life of all of the drives in total in this? Like, is there work being done to be more,
absolutely,
less about monitoring and more about actively participating?
Yeah, actively participating from the host side is definitely part of the standard right now. I mean, I'm going to talk about a couple of examples. You probably have heard about ZNS, zone namespaces. Like, this is going into the area of placing the data where the write amp is going to be the lowest.
Okay.
Right? And write amp means whenever you're writing to the flash, you have a tax of writing more to the flash than what you intended from the host. And that's, you write 2x or 3x than what the host has requested. So there's definitely, initiatives in the industry to standardize that, the placement of the data, and that's something that's we're also working on. Yeah.
Cool. Thank you.
Again, this is probably another way of looking at it. Few different applications that I talk about: content delivery network, object storage, and edge analytics. The question that I pose here is QLC SSD ready to be replaced with TLC for these edge applications? And you can see, I mean, just leave behind for you guys, P5430 and P5336, both are our latest generation QLC drives. And you can see across the board in these workloads, and the last workload is pretty interesting, which is write pressure test. Think about on the edge, you're doing multi-tenant. While you're ingesting some data, you want to access something real quick, real time. Can the device support those real time access at a very, predictable SLA, low latency, in other words? And in those type of workload, across the board, you can see that the QLC SSDs is actually leading, or basically, better than the incumbent TLC in the market. Again, so going back to your point about the reliability aspect of it, right? So 0.44% AFR and annual failure rate has been the de facto, right, failure rate in the field. So we are actually trending much lower than that. You can see our first generation, second generation, and third generation. We are our third generation QLC SSD. We're much lower than the industry standard, and that means, okay, from a TLC versus QLC deployment, there's not much difference in terms of reliability because they're actually basically using the same controller and the same goodness. And not only that, silent bit corruption is another area that very, very near and dear to people's heart who are really, really looking into quality and reliability, right? And this is a bit flips silently and the drive did not recognize. That results in, data corruption, that results in revenue loss or other catastrophic failures, right? For mission critical application that is of utmost importance. So within Solidigm, all of our SSDs are protected with ECC and CRC. All the different memory elements are protected. The firmware also provides some robustness around it. And not only that, we take these drives, we take it to Los Alamos lab, maybe like twice a year or once a year, Roger? Once a year, we take it there with a batch of other SSDs in the market, right? Competitive SSDs, and we actually, bombard them with neutron beams and see which drives actually is showing zero silent data corruption because that is kind of the purchase criteria for a lot of tier 1 CSPs. And you can see that our drive is trending the lowest in the pack in terms of the projected AFR, NO failure rate in these tests. Not only that, it also had zero silent data corruption in our tests. So that's something that we have been showing on over a few generations now. So this is another way of looking at it. Switching gear and going back to the monitoring, the reliability, the security part that you talked about, and the manageability stuff, right? So taking advantage of the core features of the SSD and translating it to the edge is what we want to do here, right? So basically, we want to make sure that at the edge, the temperature logging, the health logging, those features are robust. You can, look at the wear out of the devices. We provide, advanced features to look into the NAND level failures, which is the program and erase cycle count and program and erase errors that is happening on the fly, reporting back to the user. And not only that, we can also out of band access the device, right? So while the IO is running, you can poll it. There's an industry standard around it. It's called NVMe MI, management interface, through which you can actually do an out of band polling on the device. And not only that, not only polling, you can actually change some of the characteristics of the devices. Say it's getting hotter, you can actually run it on a low power mode, right? You can change different throttle modes there. So there's a whole bunch of analytics that the drive can provide, and also controllability that the drive can provide, because the drives are at the edge. So you need more and more manageability. You don't want to, roll in a truck and get those fixed, right? So that's one thing. The other thing is on the security side, there's lots of thing happening, right? So start from the very basic. Drive level locking is there. And modern devices also have namespace locking. Like you can have different namespaces allocated for different tenants, right? And then you can lock them. In future, we will also do IO locking, like, which we call the key per IO. Each IO can have its own key from a key repository from the distributor. So again, thinking about, supply chain management, inventory management, even IO management at their core to the edge. We're trying to get those features in place for that. Not only that, a device at the edge, the device attestation, say you have a device, is it your device or not? Having that attestation framework in place is also very critical, and that's part of our feature offering. And the feature is about post-quantum crypto, where all of these can be broken, and that's where the post-quantum crypto algorithm and hardware will come into picture. The other thing that I want to talk about here is the drive self-test. Remotely, you can actually initiate a drive test on the device, right? And you can also do it out of band, and the drive will actually tell you, hey, is my cap that protects against power loss, is it still working or not, right? At that level, is my DRAM in the device is working or not? What is my power governing? Can I change my power governing on the fly? So anyway, the host of good things that SSDs already provide, and this actually gives you another way of extending those for the edge. Here I'm going to talk about 3 examples of edge deployment that is right now. You can find it. Dell PowerEdge XR12, right? So they're using TLC SSD, SATA SSD. So on a conceptual basis, I think we have created a configuration where it can be replaced by 61 terabyte, the one that Jeannie's already talked about, SSD. And that gives us a few things here. One is it increases our capacity, right? You can see the bandwidth increase up to 6 million IOPS. It gives you IOPS per watt improvement. And going back to that locality challenge, weight and space, it gives us tremendous amount of gigabyte per centimeter square and the gram per terabyte, right? So those are important locality metrics that needs to be paid. We need to pay attention to those when we deploy for the edge. So that was just one example for the edge infrastructure. This is another example where legacy HDD-based server, Gen 10 from HP ProLiant, they're using 4 terabyte SSDs, right? HDDs, right? So that can be replaced by 4 E3.S, which is the slim form factor QLC SSD, and that gives you, again, tremendous amount of density growth, good space and weight optimization, higher performance, absolutely basically you can imagine 4 HDD versus 4 QLC SSD comparison here, and really high endurance level. Last but not least, this is an endpoint edge server example. Think about that your telco tower or wherever this can go on, right? Right now, the incumbent is M.2. M.2 has a lot of challenges, it's not really hot pluggable. It has limitation on capacity. The capacity growth is not there. It cannot also go to, beyond higher PCI interfaces, right? So from all those point of view, going to an E1.S based design and embracing a QLC will be the right choice here. Although the performance numbers are very close, coming very close, but again, if you think about future design, E1.S will be the perfect form factor for this type of deployment. So last but not least, I have to move it to Jordan real quick from Storage Review. But before I go, I want to talk about, we have come a long way, right? From our first generation SSDs, where the OEM stopped talking to us if we do not have 20 drivers per day drive, right? And look at now, it's 0.5 drivers per day on a lot of our QLC devices, and still the endurance level that is required for the applications, we are beating them by quite a big margin, right? So we have come a long way in terms of endurance evolution. So the thing is, it's time to embrace those cost efficient, sustainable QLC-based devices, not only for the core, but also for the edge. Performance with impact. I've showed some performance numbers where we have seen that from the first generation SSDs where garbage collection was a problem, write amplification going through the roof was a problem. Those things are better understood now. So we are in a better position to deploy them in places which is a little bit unknown to us from a workload point of view, because the devices have gone smarter and managed themselves better. And going forward to your question, we will get more of this controllability back to the host so they can actually lay their data the way they want it if they have that infrastructure in place. Form factor, big revolution there. I mean, most of our drives, we don't have a U.2 one form factor fits all type of solution anymore. We have a full portfolio. So if you're a slim, Lenovo type, ThinkServer or local server, you can think about E1.S. If you have an object scale, you can think about E1.L, right? So there's multiple things that is happening in that space. And last but not least, the data-centric features going to the edge, we would need some predictable analysis, right? So giving them, good data on the smart or good data on the monitoring, and let them analyze that data and predict the failure mechanisms and try to replace the drives in time. Those will be critical for the future. So I think we're ready. The evolution has taken us a long way. I mean, we have gone a long way from, playing on the bowling alley and really going and deploying some of these on the next gen tractors and, ADS systems. So